So let's start with my presentation. First of all, a short overview about the collaboration between MF Software and Beaumont. So we started our partnership in around autumn 2018. And since then, MF Software is the exclusive European sales representative for the three products or services that you can see here. It's on the one hand, the MeltFlipper Teknolojisi, which is an optimization of the runner design to avoid unbalanced filling in most of the cases in multi-cavity tools. This is the topic that we want to deal today. Then there is a second product or service. It's called ThermoFlow, which is a material characterization method where the flow behavior of the plastic material is measured directly during the injection molding process. The benefit is that the results are closer to the real behavior in an injection process in comparison to, let's say, conventional methods like the measurement in rheometers, which is more related to an extrusion process because, for example, things like frozen layers are not taken into account. And so this is a measurement here which was developed by Beaumont and which takes these things, these typical things like frozen layers, which are playing a big role in injection molding processes into account. And so this is, let's say the first measurement method for direct characterization in an injection mold. And the third point here is the official mold flow material characterization service, which offers material testing and creation of the UDB files for the use in the mold flow software. But today we want to have a look at the MeltFlipper technology. The technology as such is not really new because Beaumont sells this solution successfully for around about over 30 years now. But what is the background, or what are typical cases where it's reasonable to use this technology? Have a look at these two pictures. You see a short shot of an 8-cavity mold with a cold runner system. We can see that all runner sections for all cavities have an equal length, equal diameter. Venting is not a problem here, so we expect a balanced filling. But the reality shows that this is not the case. The inner cavities are already more filled with material than the outer cavities, or in other words, the inner cavities are filled faster. So what is the reason for this effect? To understand that, we have to bring back some total basics of plastic flow behavior to our minds. We know that plastic is a non-Newtonian material and that it's laminar flowing, that it is shear sensitive, and in a flow channel, it is subjected to high shear forces, especially in areas near the wall. This is what we can see here. And this leads to, let's call it donut geometry in the channel, which means that we do not have a uniform shear affection of the material over the cross-section of the channel. You can see this down here in this picture. This is the, let's say, donut geometry that I was talking about. What does that do with our material? You can see that here. We have high sheared material in areas near the wall, and we have lower sheared material in the middle area. Material which is affected by high shear forces reacts with becoming hotter, so the temperature increases. And as a second effect, the molecular strains are degraded. Especially the second effect is somewhat different in its intensity depending on the material. But the total result, meaning the decreasing of the viscosity, is a combination of both effects. So what happens when it comes to a branch or a split in the runner? We can see that in this picture. We get a non-uniform viscosity distribution over the cross-section of the channel with a, let's call it left-right imbalance. I will show this again with my hands, so hopefully you can see me now in my camera. Think about this donut geometry. I will do that with my hands here, and we go through the runner, and we come to an intersection now, to a branch. And what happens to the melt? It's splitted, and we can see here we have the high sheared in the outer areas, high sheared material, laminars in the outer areas, and we split it now. And then we see that we have this left-right imbalance in our runner system. So you can see here we have high sheared material in the inner areas, let's call it that way. And we have a lower sheared material in the outer areas. So that means we have a non-uniform viscosity distribution over the cross-section here. What people observe, especially in multi-cavity tools, then are different results of this just explained effect. Maybe they see different warp results between the different cavities, which comes from different packing distribution in the complete tool. Maybe they observe short shots like I've showed you before in these pictures. Sometimes they have surface defects. I have an example on one of the next slides. They can observe differences in weld line strengths, for example, because when weld lines are formed in the parts, they are formed in cavities with hotter material. They are formed with hotter material there and with colder materials in later filled cavities. Sometimes core shift is a problem. I will also show you an example later. Or they can observe things like air traps, which is an example here. And what do people often do in industry when they are confronted with these effects? Often they make a trial and error. They want to modify runner and gate diameter to achieve an equal or unbalanced filling. They maybe optimize gates, they work with higher injection pressure, with higher packing pressure. But maybe they reach a goal to get an equal filling, but they still see problems. Problems maybe with freezing, problems in the packing, so the risk of blowholes and warp issues. They have, of course, higher process expenses when they work with higher pressure and higher clamp force requirements then, and they decrease their process window. So maybe changing diameters in runners and gates can lead to an equal filling of all the cavities, but often you still have unequal part quality. Here you can see the first example of this effect in 4-cavity mode. In this case, the effect leads to a, let's call it in-cavity imbalance. Remember what I showed you with my hands. Start here at point 1 with the donut geometry and see what happens when the viscosity see what happens with the viscosity distribution after the branch at point 2. You have the higher sheared material in the inside here, so this flows into the inner area of the cavity, and we have the lower sheared material, so the colder material, slower flowing material here in the outside of the cavity. So we have different temperatures. We have a temperature distribution which is not equal over our cavity. And we have also a different filling speed. Here you see the example from the one I showed you right in the beginning of this presentation. That's the 8-cavity mold, where we observe the cavity-to-cavity imbalance, but also the in-cavity imbalance. Yeah, you can see that here. We have also an imbalance in the cavity as such. So the inner areas fill first. And we have then, a very strong imbalance between the inner and outer cavities. Again, try it by your own with your hands. Yeah, from the donut geometry at point 1, go through the runner until you reach the cavity, and you see where these effects come from. So, what is the MeltFlipper technology now? The idea is to rotate the melt at a branch around a certain angle to change from the, we called it left-right viscosity gradient or left-right difference in viscosity, to an up-down difference. This is achieved by designing a height offset in the channel at each branch. The exact design of this height offset is depending on different parameters like the material, or better to say, on its shear sensitivity. It depends on the flow length, the runner size, the cavity volume, etc. That means that the MeltFlipper geometry, so this height offset to achieve a rotation of the melt in the channel, is designed individually for every mold. Every application, or every part, every mold, every tool needs its own design to reach this goal. And Beaumont has developed a method to generate these designs, which is, of course, their own knowledge. We at MF Software also do not know how they determine the final dimensions of the design. Yeah, so you can see this here. This is a change in the runner design. It's a height offset which is brought in, and this height offset leads to a turning of the melt, to a rotation of the melt, to come from this left-right viscosity difference over the cross-section of the channel to an up-down difference. And an up-down difference is not that problem, because we go into the wall thickness of the part then. And there we do not observe these problems like we've seen them when we have still this left-right imbalance. So what do customers get as benefits when they use MeltFlipper technologies in their tool? On the one hand, we have the quality potential. So the viscosity differences are compensated. That leads to a balanced filling of the multi-cavity tools. This leads to optimized warp, elimination of short shots. In total, it leads to an increase of our process window, and it leads to a similar part quality. We also have here in this picture a real example of that. You can see on the left side, these 4 cavities are filled without a MeltFlipper geometry here in the channel. And on the right side, the MeltFlipper geometry is brought in, at this branch and at this branch here on this side. And you see here an equal filling of all the cavities. On the other hand, we have then also the saving potentials, like the reduction of the cycle time, when it comes to cooling time or packing times. We have a reduction of pressure and clamp force requirement when we do not have to compensate this unbalanced filling by higher pressures, and with that coming higher clamp force requirements. We have, of course, the elimination of scrap. So in total, we save time, and of course, we save money. In here, the bottom right corner, you can also see that this technology also works for single cavities. This is a special application, but especially when it comes to such geometries here, where we have this disc geometry, let's say. We have a faster filling in the outer areas without the MeltFlipper, but here it's also possible to rotate the melt. And so to rotate it in that way that we fill the inner parts or the inner areas of this cavity first. And so to avoid an air trap here and in general to avoid a more equal filling of this part. So it's also possible to use this technology in some special cases or special applications in single cavity tools. Yeah, this leads us to the benefits as such. So we will achieve a homogeneous melt temperature, homogeneous supply of packing pressure. That means no difference in warp between the cavities. We can eliminate maybe core shift issues, which are caused by asymmetrical filling. We have no increase in pressure and clamp force requirement. We reduce our scrap. In general, it is possible to control our melt flow, even also in single cavities, which means an influencing maybe also on the time and position of weld lines. And yeah, of course, the prevention of air traps. This is what I showed you here. As I said, here is an example when it comes to the core shift issue because of this unbalanced filling or unequal filling of the both sides of the core, especially in such high standing cores. This may be an issue. Here you see how this looks like when MeltFlipper geometry is implemented there. This is another example. So we have two temperature sensors brought in here. This is this green and brown point on the geometry in the tool, and the temperature of the melt was measured during the process. Here we have a conventional, they call it conventional runner system. So that's the runner without any MeltFlipper technology. And here in the bottom we have the runner with the MeltFlipper technology. You can see here the roundness or concentricity of this part. Yeah, this is a gear here, and you see that the concentricity is really better for the one with the MeltFlipper technology brought in. And what we can also observe is that we have a temperature difference between those two temperature sensors, which is in the conventional runner system of about 21 degrees Celsius. Here, those values are in Fahrenheit. But in degrees Celsius, we have a temperature difference of 21. And with the MeltFlipper technology, we reduce this to only about 3 degrees temperature difference. Here is an example of simulation results of this effect, which were simulated with Autodesk Moldflow. And it's a comparison. Again, on the left side, we have without the MeltFlipper solution. On the right side, we have the MeltFlipper solution brought in. This is the temperature distribution, especially in the runner system here. And you can see on the red color here that we have hotter material on the inside cavities, and we have a more equal picture of that on the outer cavity, or a more equal picture of that when MeltFlipper technology was brought in. It is important to say that it is not really easy to simulate this effect in Moldflow. The reason is I already told you that we have two causes of these effects. One is the increase in temperature. This is possible to simulate here when the mesh is fine enough. Yeah, that's really important to say. You need a very, very fine mesh. So temperature increase, that is possible to simulate. What you can not simulate is the degrading of the molecular chains. So this part of the effect is not possible to simulate, and so you will see this effect not that strong in simulation like you will maybe observe it in reality. Yeah, this is important to know. So what is the workflow then if you say, okay, we have an application here and we want to bring in or we want to try out the MeltFlipper technology? It's, yeah, really fairly easy. You send the CAD data of the runner system and, if possible, also of the complete tool or of the part to us. We will forward this to the colleagues at Beaumont, and they will give us back a short evaluation about the expected advantages of the MeltFlipper, if it's possible to bring it in your tool, if there is enough space in the complete runner areas to bring in the MeltFlipper there. This is often a problem. If there is not enough space in the tool, it's not possible to bring in this geometry change, this height offset in the runner system. So this is something that the colleagues have to look at first. And yeah, in total, they want to give the customers an idea, or maybe they want to tell them if they can expect that MeltFlipper will solve their problem here or not. And if the customer then chooses to buy this technology for their tools, Beaumont will supply the revised CAD data, so the optimized runner design to you, and together with this license certificate, which is valid for this one tool. And then for you as a customer, it's possible to bring this runner design into your tool and use it over the lifetime of the complete tool. Also important at this point is that Beaumont gives a 100% guarantee. That means if you are not satisfied, no matter for what reason, if you are not satisfied with the MeltFlipper solution, if you're not satisfied with the results, with the parts you get out of your processes, it's always possible for you to remove the optimized runner geometry from your tool again, and then you will Beaumont will refund your money, except for a small design fee, which is about I think 400 euros. Yeah, so that means that Beaumont is, of course, after 30 years, really convinced about their technology, and they know that it works. And so it's no problem for them to offer you and tell you if you are not satisfied with that, it's no problem. Just remove the geometry from your tool and you will get your money back. And I can tell you, as long as we are dealing with MeltFlipper technology, we had no customer who has done this until now. So again, what are your benefits? Benefits are success and quality from the first shot. And you do not have to waste your time with trial and error in gate and runner design changes to achieve an equal filling, to achieve an equal part quality. You can use MeltFlipper, you can save costs, time, and increase your part quality right from the first shot. Okay, that's what I wanted to present you about the MeltFlipper topic.